Okay, my name is my research title is Investigating the Impact of Process Parameter on Quality of Injection Molded Plastic Engine Fan Blades using a Moldflow simulation study. So, the injection molding process is widely used in the manufacture of plastic components, including engine fan blades. To achieve optimal performance and quality, it is crucial to carefully select and optimize process parameters. In this study, a parametric investigation of the injection molding process for plastic angle fabrics was conducted using Moldflow simulation. Solidworks software was utilized for part modeling, and the simulation results were analyzed to determine the impact of various process parameters on the final product's quality. The result of this study have important implications for the optimization of the injection molding process for various plastic components. Introduction, let me explain about the frame blades. The frame blades is one of the specially shaped rotating parts blades of a mechanical fan that move and distribute air. The plastic fans are better than metal fans for smaller application and in the home. It's due to their durability during manufacture, their wear, tear, and tear less. They are more lightweight and put less pressure on the motor, and they are quieter due to the fewer vibration than the metal fan. The current industry uses polypropylene and composite plastic resin or polymers to make plastic fan. However, designing polymer composite metal parts is challenging due to the drop in their strength properties caused by mechanical impact damage. So methodology. First, we go to SolidWorks modeling. To ensure compliance with market standard, the actual size of the axial fan need to be studied and measured in order to determine both in real and maximum size. To create the 3D model of axial fan, the SolidWorks software is utilized. The design of the axial fan is developed using the software, and the resulting 3D model is saved in the IGS format. This format is compatible with Moldflow software, which will be used in the subsequent stage of the research. Figure 2 shows the 3D drawing of an axial fan. And then we move to Moldflow process. So for the analysis with auto there's Moldflow software simulation assists us to optimizing the injection molding process. Designer, I use this software to build the mold using a simulation setup and inquire result to identify mesh statistic, gate position, material selection, molding windows analysis, field analysis, and how to fit system and geometry effect product manufacture. To load the product into the Moldflow software, the part must be in IGS file format. After loading the product into Moldflow software, the following step is to mesh the product design. Figure 4 depicts the axial fan after meshing was generated in the Moldflow software. After the meshing procedure was done, the placement of gate was determined. The models recommend part position. The model recommend gate position for the axial fan is shown in figure 5. Then we move to levels of designing parameter. So there are four independent parameters that are applied in simulation, namely as mold temperature, melt temperature, injection pressure, and injection time. So each factor have five levels, and each level will be entered into the Moldflow software during the process setting. While the value of L3 factor L3 level will remain constant, the value of the other factor will fluctuate as shown in table 1. As you can see here, the table, there are four factors of temperature, melt temperature, injection pressure, and injection time. So there are 5 levels for each factor. So what we say that in level 3, we use as datum. For example, um, for running one, for run one, we use 40 degree for more temperature, and the rest factor we will use the L3 value, which real temperature of 260 degree, ignition pressure of 120 megapascal, ignition time of 1.5 seconds, and it goes to the all and run. Okay, so it's called as one factor design, often known as one factor at the time OFAT, employed in this parametric investigation to ascertain if if a specific element impacts output of or reaction. This method enables us to examine the factor's impact in great depth, and it aided in determining if a change in output in the simulation results is caused by a change in the output levels effect or not. So here are the results and discussion. So there are four results, which means determine the four factors that we are studying here. The first factor is factor A, more temperature. As we can see here, the figure 6 shows the result of more temperature versus shrinkage. Based on the result, more temperature gives an influence and effect on deflection of material. As can be seen in the graph of more temperature versus shrinkage, the higher the higher the value of more temperature, the greater the value of shrinkage at the material. Okay, and then we move to figure 7. Figure 7 is the warpage. At the warpage, x-axis and y-axis gradually increase, but the warpage and z-axis initially increase before its value decrease at the end. Okay. Rise in more temperature causes less condensation of the plastic inside the cavity, which makes it easier for the melted plastic to flow inside and produce parts with higher part weight and better surface qualities. So we can conclude that the more temperature is one of the injection parameter influence that may cause warpage in the injection molded polymer. And then we move to factor B. Factor B is melt temperature. So figure 8 shows the result of melt temperature versus shrinkage. Demonstrate that the value of shrinkage at the material increase as the melt temperature increase as well. It indicates that the temperature rise by 10 degrees Celsius, and there is also an increase in the percentage of shrinkage, with estimates ranging between 0.3% and 0.35%. So in figure 9, it will show that warpage this differs significantly from warpage in x-axis and y-axis. In contrast to warpage y-axis, which rise initially but falls off at the completion of the experiment, and x-axis which rises relatively gradually. Warpage z-axis shows a mirror increase. Viscosity decrease as melt temperature rise. If it's too high, resin will be excessively thin and unable to completely fill the mold, leaving an incomplete product. Then we move to factor C, injection pressure. The simulation was set up with a variety of injection pressure, 100 megapascal, 110, and 130 and 140 megapascal, with constant factor setting of 1.5 second injection time, 260 degree melt temperature, and 60 degree mold temperature. The result from the injection pressure has no significant impact on shrinkage of the material during injection molding. Increasing injection pressure does not change the value of shrinkage, indicating that it is not it is not a crucial factor in the experiment. And then we move to the last factor, factor D, injection time. According to figure 10, the variation of deflection value are not consistent and it initially increases and decreases before increasing again. They are fluctuating. So the graph indicates that the shrinkage value of the material can increase or decrease as the injection time is increased. It demonstrates that the result won't progressively grow or decrease as the injection time is increased. The pattern of warpage value for x-axis and z-axis is shown in figure 11. Values initially increase, then decrease in the middle before rising again towards the end. On the other hand, the warpage value for y-axis is initially high, then decrease in the middle and finally decrease again towards the other hand, the warpage value for y-axis is initially high, then decrease in the middle and finally decrease again towards the end of the simulation. So in conclusion, we can conclude that the study examined the effect of four parameters in the modeling process of axial fan made polymers using Moldflow software. The selected parameter were mold temperature, melt temperature, injection time, and injection pressure, while the response of interest were warpage and shrinkage. So the one factor design was employed to assess the impact of each parameter on the response variables. The injection time parameter was found to have an impact of both shrinkage and warpage of the material during the injection molding process. As injection time increased, the fill time also increased, resulting in unstable percentage of shrinkage in the material. The injection time also influences warpage by affecting the speed at which shrinkage molecules pulls during the chilling process. The melt temperature factor has an impact on shrinkage and warpage. Increasing the temperature creates space for defects, but if the temperature is too high, the viscosity increases and the mold may not be filled. This set point. Injection pressure has the least impact on the response option in this research. Different injection pressure values have no effect on the response option, which consistently produce similar readings. However, injection pressure is an important factor that needs to be controlled in other research, as it could be influenced by different design and material. Overall, the study's result provided suggestions for the optimization of product and process parameters to enhance the plastic axial fan rates overall quality. The implication of this finding are crucial for optimizing the injection molding process of other plastic components. That's it for me. Thank you.